If you've taken a physics course before, you've seen these four equations. They're called the kinematic equations, and they describe the motion of an object traveling in one dimension with a constant acceleration. And the way they're written here, we've defined our coordinate system so that our initial position is 0 and our initial time is also 0. These equations are useful because they each have a different set of variables present, meaning that you can look at what you already know about a problem and pick the correct equation that has what you know and also the variable that you want to learn about. The problem with these equations, though, is that they're sort of hard to remember. They don't all make complete sense when you first look at them, and they're just somewhat difficult to memorize. So in this video, we're going to use two simpler, more intuitive relationships that will actually lead us back to these equations, just to try to minimize what we have to memorize. The first simple relationship we're going to use is the definition of velocity. So we know that velocity equals the change in distance divided by the change in time, right? So this is x minus x naught, the initial position, divided by t minus t naught. And then if we let this difference in time go to 0, take the limit as this goes to 0, this is the definition of a derivative. So we get that dx dt is equal to the velocity. And this is the basic definition of velocity. And the second relationship that we're going to use is the definition of acceleration. So we have acceleration, it's similar to velocity, but the change in velocity divided by the change in time is equal to the acceleration. And so we'll rewrite this the same way we did up here. V minus V naught divided by t minus t naught, which is the initial time. And then if we take the limit as the difference in time goes to 0, we get the definition of a derivative again, and we get that dv dt equals acceleration. So how do we take these two more basic relationships and turn them into these useful equations that we know and love? Well, first of all, I've written this definition of acceleration in green for a reason, and that's because this kinematic equation here that's also written in green is actually just the definition of acceleration. So if we take this and we rearrange it, and we've defined our coordinate system so that the initial time is 0. So this is 0. We get, I'll just rewrite it. A equals V minus V naught divided by t. This is the initial velocity. And if we rearrange this and we solve for v, we get v, the velocity at a certain time, equals the initial velocity plus the acceleration times time. And so we've already gotten our first kinematic equation. It's just the definition of acceleration. And I've forgotten my subscript 0 here to specify that this is the initial value of the velocity. So now that we have our first kinematic equation, let's work on getting our second. And the second one we'll go for is this one written in yellow here that deals with the position as well. So to get this, I'm going to rewrite this equation here, but use the definition of velocity. I'm going to substitute that in here. So instead of v, I'm going to write dx dt equals v naught. So the initial velocity is not a function of time, it's just we've picked that time as our reference, and this is our reference velocity, v naught, plus acceleration times time. Now, to solve this for the position, we're going to need to integrate with respect to time. So, integral of dx dt the integral over time of dx dt equals the integral of the velocity, initial velocity, plus the integral of the acceleration times the time, integrating all of them over time. For our limits, we'll put t naught to t. So our initial velocity to our final velocity. So first I'll solve the left-hand side. We're taking the antiderivative with respect to t of dx dt, which is just x, and then we're evaluating it between x of t, and we're subtracting x of t naught, our initial time. So this is our left-hand side. And so x of t, we're using that as x. This is just our general position variable, which is a function of t, but we're not explicitly showing it's a function of t all throughout these equations. So I'll just write it in this simpler form. And then x of t naught, which is our initial position, we defined up here. We said initially that we're defining our initial position to be 0. So I'll just cross this out. That's just 0. So our left-hand side is just x. So now let's solve the right-hand side. So since we just picked our initial reference moment and our reference velocity, this v0, our initial velocity, doesn't change over time. It's just the velocity at the certain time we picked. So this is a constant that we can take out of the integral. So v0, and then when we integrate dt, we just get t that we evaluate at our limits. So this is t, so velocity, so our initial velocity times t minus t naught. And then over here we get a, our acceleration is also constant because this is, the kinematic equations are valid when the acceleration is constant. And so in keeping with that assumption, we will treat acceleration as a constant. Acceleration times the integral of t. So the antiderivative of t is t squared over 2, and we're evaluating it at these limits. So we're getting, this term is the acceleration times t squared over 2 minus t naught squared over 2. And this is our right-hand side. So since we've defined in our coordinate system that our initial time is 0, I'll just cross out the t naughts, and then so we get this. The right-hand side is v0 times t plus the acceleration times t squared over 2. And so if we combine our left-hand side and our right-hand side, we get x equals the initial velocity times time plus the acceleration times the time squared divided by 2. And this is our kinematic equation that we wrote in yellow to begin with, right up here. So we've actually reproduced 2 of our kinematic equations. And now, actually, I'll go back up here. So now that we have these 2, let's try to get this equation so that we have a useful equation for when we don't want to know, or we don't need to know the acceleration. So we'll use what we know to try to get this equation that sums up what we know, but leaves acceleration out of the picture. So how can we do that? Well, to do that, we'll take our definition of acceleration, we'll solve it for acceleration, and then we'll substitute that value or that expression for acceleration into this equation, and then hopefully this will pop out. So let's try that. So first I'll rewrite the green kinematic equation. So we have v equals v naught plus a times t, acceleration times time. So if we solve this for the acceleration, we get acceleration equals, so we subtract v naught from both sides, v minus v naught, and we divide by t to get a by itself. We get this right here. A equals v minus v naught divided by t. And now if we substitute this in here, let's see what that gets us. And since we're going for the blue equation, I'll write it in blue. We get x equals v naught times t plus, so we're substituting this expression for the acceleration into here. So we're going to say v minus v naught over t times t squared over 2. So we have a t in the denominator and a t squared in the numerator. So I'm going to cancel these, and then I'm also going to separate this sum here. So I'll rewrite this. X equals v naught times t plus v times t over 2. That's this first term in this sum. I'm distributing this t over 2 into this difference, minus v naught over, v naught times t divided by 2. So now I have two terms that have v naught times t in it, so I'll rewrite this. I'll rewrite the v times t. This is our velocity at a certain time, t, plus we have two terms that have v naught times t, the initial velocity times time, and then I'm going to factor out this v naught times t and have 1 minus 1/2. And 1 minus 1/2 is just 1/2. So simplifying just a little bit more, we have v times t over 2 plus v naught times t over 2. And now if we factor out this t over 2 from each term, we get x equals v plus v naught times t divided by 2. And now if we look back up top, you see that matches our goal of finding this kinematic equation written in blue that doesn't have acceleration in it. So here's our third kinematic equation. And now let's think about what we have to do to get our fourth kinematic equation. So we have these three. What do we want to do to get the fourth? Well, we're trying to eliminate this t, right? This equation doesn't have a time term in it. So we need to find some way of taking what we already know and eliminating t. And it might not surprise you that the way I'm going to do this is I'm going to go back to this definition of acceleration. I'm going to solve it for t, and I'm going to plug it in here so we can get rid of this t term and hopefully get something that looks like this. So let's go back down here. So we have this equation, and I'll rewrite the definition of acceleration once more. In the form of the kinematic equations, we have v, the velocity at a certain time, equals the initial velocity plus acceleration times time. If we solve this for t, we get, so we subtract the initial velocity over v minus v naught, then we divide by the acceleration this time to get the time alone, divided by acceleration equals t. And now we're going to substitute it back into the equation we just found and see what we get. And now I'll write in red since that's the color of the equation we're trying to find. We get x equals v plus v naught over 2 times this expression for t that we got over here, times v minus v naught divided by a. So here's our new equation, and let's try to rearrange it to get it to look like the one up top. So first we'll multiply both sides of the equation by 2 and by the acceleration. So we get 2 times the acceleration times the position equals v plus v naught times v minus v naught. So if we FOIL this, we get the first term is the square of the velocity, and then this is the order I like to do it. I like to do the first two and then the last two. So I'm going to do this one first and then this one second. So we get a plus v naught minus another v naught, or times a negative v naught. So we get minus v naught squared. I'll do this term. We already did that term. And now I'll do this term. So you get a negative v times v naught, v times v naught. And now this term. I get a v naught times v naught times v. Well, these two are the same, but just negative, so they cancel each other out. And we're left with the square of the velocity minus the square of the initial velocity. And now we can rearrange this and get v squared equals the initial velocity squared plus 2 times the acceleration times the position. And this is our fourth kinematic equation. And so now we've reproduced these 4 kinematic equations just from these 2 simple relationships. And at each step, all we've done is we've built an equation, and then we've taken what we know and we've added to it using our definitions. Now let's think about what the advantage of these 2 simple relationships are, just using these. Well, first of all, they're much easier to remember since this is just this simple definition of the change in position divided by the change in time. It's how we're used to thinking about this. And similarly for acceleration. And another advantage of this is that to get these equations, we used a specific coordinate system where our initial position and our initial time were 0. And we also assumed that our acceleration was a constant. But you can apply these equations to any coordinate system, and even in situations when the acceleration isn't constant. So basically they're easier to remember and they're useful in more situations. They're more general. So this video really had 2 purposes. First, it was to show you that these equations that you probably used before, show you where they come from. The other purpose was to show an example of the main goal of physics. And the main goal of physics, or really any science, is to come up with the simplest relationships that we can use to describe the world we live in. So hopefully you've enjoyed this video a little bit, and I'll see you soon.